Hi, welcome back to the Mathematics channel, the only channel on YouTube where we are absolutely addicted, frothing at the mouth for math. Now, today's video is going to be about Gaussian elimination, a very interesting topic in linear algebra with various applications. Now, this topic might seem confusing or convoluted, but today we're going to understand it in the simplest and most intuitive way. And I guarantee that by the end of this video, you will be an expert in the foundations of Gaussian elimination, as well as its numericals. Now, notice how I'm focusing on the foundations and numericals this video. I also plan to upload subsequent videos, maybe going in depth on certain topics like ranks or null spaces or pivots. I also am definitely going to upload a video on the geometric interpretation of Gaussian elimination, how it looks visually to perform Gaussian elimination. It's going to be a very insightful and crazy video, so I highly suggest that you stick around for that. Also, before we start, I suggest and I recommend that you have a basic understanding of linear algebra. I don't care where you get it, can be from courses, YouTube, books, anywhere, but you should have a basic understanding. Let's begin. Before we understand Gaussian elimination, we're going to understand what problem are we trying to solve using Gaussian elimination. And the main problem which we try to solve in most of the numericals is solving a system of linear equations. Like here, we have 3 linear equations in 3 variables. This applies to n number of linear equations in n variables. But most of our examples and most of our numericals focus on 3. So we're going to be doing that too. But just know, this applies to n number of equations in n variables, not just 3 equations with x, y, and z. Now, what are we trying to do? What do I mean by solving these equations? I want to find x, y, z that satisfies the 3 equations, right? That's all I want to do. How are we going to do this? Before we learn how we do this using Gaussian elimination, we're going to first transform this set of equations into a matrix form. Gaussian elimination works best in matrices and matrix forms. So I'm going to do a recap of how we transform this set of linear equations into a matrix form. But you should already be knowing this. Let's say I want to transform the left-hand side of the first equation into a matrix or vector form. How do I do it? Since it's just a linear combination, sorry, the left-hand side, since it's just a linear combination, I can just take 2, 3, and 4, which are the coefficients, and x, y, and z, which are the variables. What happens when I do multiplication on this vector with this matrix? The first row is multiplied by the first column, which is x, y, and z. So we get 2x plus 3y plus 4z. This is literally what we wanted. Now, this is what we get when we do the multiplication. What if I make the equation like this? The same thing, but I write this as equal to a vector with the answers, or the right-hand side, 1, 2, and 3. So this thing which you get by multiplying should be equal to our answer, which I've written, which is 1. We've just written the first linear equation in the form of matrices and vectors. To write the rest, same thing. Just write all the coefficients in the left matrix. The variables are, again, the same. No need to change that. And the right side should just have all the answers. Look what we did. Multiplying this matrix by this vector will give us the left-hand side here, left-hand side here, and left-hand side here for our 3 equations. And since we have it equal to the values, we've just transformed this set into this. more formally, basically saying it in the form of fancy math. Let's say we're given a matrix A. It could be anything. And the vector B, which is our right-hand side. Again, in this, what are we given? We're given A, we know the coefficients. We're given B, we know the right-hand side. What are we trying to find? I said earlier, we're trying to find X, Y, and Z, right? We're trying to find this. X, Y, and Z is just conveniently written in this vector. So what are you trying to find? We know this, we know this. We're trying to find X, Y, and Z. It's the same thing written in fancy math. So we have the matrix A. We have the matrix B, which is just the right-hand side, whatever the answers are. Sorry, we have the vector B. Now we just need to find the unknown vector X, which has X, Y, Z, whatever, all the way up till however many variables. Writing this in the most simple way, A is a matrix, X is the vector, it's equal to B. Thinking of this in a geometric way, we have an unknown vector and we're transforming it using a linear transformation, which is a matrix multiplication, to get a vector B. We know B. We know what happens after the transformation. We know A. We know what the transformation is. We need to know what vector X we started with to end up with B after the transformation. That is exactly what we find using Gaussian elimination. Gaussian elimination basically removes this A, inverts this A, makes it so this never existed. If this never existed, if this is inverted, removed, then we simply find out, we simply have transformed everything back. We've inverted the transformation and we've gotten from B to X. So instead of knowing X to B, we'll find B. We'll find X from B instead of right now knowing what B is and not knowing X. How do we do this? Well, first we need to understand a sweet little notational trick that is called the augmented matrix. This is nothing but stupid fancy math. What do we need to do in Gaussian elimination? We need to basically find our answer X by multiplying both sides of this equation by the same values. Again, we don't need to know what Gaussian elimination is yet, but basically we're just multiplying both sides by some sort of matrix and eventually getting the answer through this. We'll see the details later, but this is basically what it is. Multiplying both sides basically means I'm multiplying A, multiplying B. So what is an augmented matrix? We take A, we take B, and just write them together. So A and B. I've just written them together and separated them by a line so that I don't get confused. I've just taken A, literally just taken A, and taken B and just written them together. That's it. That's an augmented matrix. This lets us easily manipulate both of them at the same time instead of doing it separately. Now we're ready to move on to Gaussian elimination. Now, the goal of Gaussian elimination, or I would say the first half, maybe like 70% actually, is to form a row-echelon matrix. Now, echelon comes from the French military, so maybe I should call it echelon. Echelon. Barring the racism, the French military organized their troops in the form of a staircase for tactical reasons, and this formation was called the echelon, and it somehow wriggled its way into math. But basically, that is what we're trying to make our vector look like, a bunch of little staircased French people. So the general form, the general visual way an a row echelon matrix will look something like this. X can be anything, whatever number, but the bottom half should be a staircase of zeros. So it should be divided somewhat like this, a staircase. Now it doesn't have to form such a clean staircase always. This is just the general form. But intuitively, it should look somewhat like a staircase. So anything like this works too. This is also a row echelon form. Notice how we're forming a staircase of zeros. It's not the best staircase, but it's still a staircase. You'll be easily able to identify a row echelon matrix by looking at it directly. But these are just some formal rules to understand it, just fancy math. The first rule, the first non-zero entry in each row is strictly to the right of the first non-zero entry in each earlier row. So let's say this is 1, 2, 2. The next row cannot have a non-zero entry here. So this can't be 2. Notice how 1 is the first non-zero entry, the leftmost one. So everything below it should be a 0. It can be, I can put a 3 or whatever here, because again, this is below the second entry, not the first. But now looking at the second row, what's the first entry in the second row that isn't a 0? 3. So below this, I cannot put a 1. It has to be 0 below it. That is basically all it's saying. That this is what guarantees the staircase of zeros. Otherwise, our staircase will not look like this. It'll look like this. You can't even climb it. The second rule, any rows consisting entirely of zeros must follow any non-zero rows. This basically means you can't just insert a bunch of zeros anywhere. It has to be after. So it can't be 0 like right here. This is wrong, not an upper echelon, because there's an X below, but we just added a row of zeros. This is like the shittiest staircase ever. This isn't even a staircase. If this was a 0, then it would be fine. You made like a flat staircase. I don't know what I'm saying, but basically this is fine, right? You're not messing up anything. But if there's a row of zeros in between and there's a non-zero row below it, that's wrong. Fucking up the staircase. Well, that's it. That is what we have to form, a row echelon matrix. Now, forming this matrix from any random matrix is actually very easy. You must be thinking like, how the hell we take an augmented matrix? Like, what the fuck? We take this, and we're supposed to get like a row echelon matrix, or what? What? How do we do that? It's very simple. We just have to follow 3 general rules. The first rule, or the first rule as in what we can do, the rules for our actions that we can take. Basically, operations. Formally, these are called elementary operations. The first operation, we can swap any rows. I could swap the first row with the third row if I want to. So it'll just be 3, 2, 1, 0. The second row will stay the same. I didn't swap that. And the first row will come to the bottom. What I do? I didn't do shit. I just swap the first and the last row. That's it. Second, multiply any row by a scalar. So I can just multiply any row by any number, basically. I can multiply the last row by 2. Will this give me? 3, 2, 1, 0, 2, 2, 2, 3. And this last row is multiplied by 2. So I get 2, 4, 2, 2. I just multiplied it by 2. That's it. 1 multiplied by 2, 2, 4, 2, 2. That's it. That's all I did. Last one. This is the key rule that is used a lot. You can add or subtract a row or a multiple of a row to any other row. So I can take any row here, I can multiply it by whatever shit I want, and then I can add or subtract it to any other. Let's say I want to take the second row, multiply it by 4, and then subtract it from the last. It's easy. First row stays the same. I didn't do shit to that guy. Second row multiplied by 4, I'll get 8, 8, 8, 12. Right? Notice how the second row stays the same in our actual matrix though. I'm not changing it. I'm not doing rule number 2 where I multiply it by a scalar. I'm doing rule number 3. I'm just multiplying it so I can use it later. Just subtract. So I multiply it by 4 and I get 8, 8, 8, 12. Let's subtract it from the last one. 2 minus 12. Sorry. 2 minus 8 minus 6. 4 minus 8 minus 4. 2 minus 8 again minus 6. 2 minus 12 minus 10. That's it. That's all we've done. Just following these 3 rules. You can probably see how using these rules we can somehow turn this into that upper echelon form. We're going to learn the best practices for doing so later. But first, let's take our shittily written rules and define them in a more formal way. Let's look at these rules. You can see that let's look at these rules now. You might be wondering, what the fuck, you taught me 3 and now it's 4. Like, what are you doing, bro? But the 3 rules I've taught before had no mathematical issue. They were absolutely correct. You can follow that if you want. But most textbooks like to divide the third rule, the subtracting rule, into 2, based on whether you are subtracting the upper row from a bottom one or subtracting a bottom row from a top one. Let's look at these rules in more detail to understand. The first, multiply the ith equation, ith row, since each row is an equation, by a non-zero scalar lambda. That's what we're doing. This is the multiplication one. We're multiplying. The second, add a multiple mu of the jth equation to a later equation I. What am I doing? I'm taking jth equation, any row, jth row, and multiplying it by whatever number mu and adding it to the bottom. Adding it to the bottom, any. Adding it to a later equation, a later row, I. That's it. This one is the same thing. Take a multiple mu, take that to any row, and add it to an earlier equation. So this is going upwards to an earlier one. That's it. This one goes downwards, this one goes upwards. We're doing the same shit as rule 3. The last rule, exchange equations I and j. What are we doing? Just exchanging the equations, flipping the rows, exchange the rows. That's it. These are the same operations, just written in fancy math. Now, why have we written it this way? Why have we divided the third rule into 2? Well, actually, this is quite useful later on when we interpret each of these rules in the form of an elementary matrix. Now, let's look at this in the form of matrix operations. Again, don't be intimidated by the fancy math. This doesn't mean shit. This is just writing those same rules in the form of matrix operations or in the form of functions. What is I, j, lambda, all this shit? Nothing. Let's think about our first rule, which is the multiply rule. Let's do it on a 2 by 2 matrix. Let's say I want to take the first row and multiply by 2. Notice how I said 2 things. Whenever I want to do anything in this multiply rule, I need to know 2 things. The row I'm going to do it on and what I'm going to multiply. Again, look at what the function is. I, which is the row I'm going to do it on, and what I'm going to multiply. Knowing these 2 things, take the first row, multiply by 2. I can just perform this. What do I get? 2, 0, 2, 1. That's it. That's all this is. Again, let's take L. Let's say I want to take the second, or take the first. Let's say I want to take the first row, multiply it by 3, subtract it from the second. Notice how I'm taking the top row and then going down. That's what L means. Lower. We're going downwards. So taking the first row, multiplying by 3, subtracting it from the second. What am I doing? First row, multiply by 3, subtract from second. 3 things which I need now. What was L taking? 3 things. I, J, mu. Now, since J is closer to mu, that's how I like to remember that J is the row that gets multiplied. And then that whole multiplication is subtracted from I, which is far away from mu. So J is the row that gets multiplied. We're multiplying the first row. So J is 1. Multiplying it by 3, subtracting it from the second row. That's it. L213. What do we get? Multiply the first row by 3, we get 6. Subtract from the 6 and 0, subtract from the second. So the first row stays the same, just using it to subtract. 2 minus 6, 1 minus 0. Oh, sorry, 1 minus 0 is 1. That's it. I'm going to let you figure out the rest of the notation by yourself, but that's it. Multiply, lower, upper, exchange. That's all we're doing. Why have we written it in this form? Because now this lends to help us in the next intuitive understanding of turning these rules into matrices. What are these rules? They're just a bunch of linear transformations. We're multiplying or adding, and if you formally prove it, which I'll give it to yourself as an exercise, and if you formally prove it, which I'll leave the details to you as a mental exercise, you can see that all of these are just elementary linear transformations. Since it's a linear transformation, we can easily write these in the form of matrices. Now, to write any sort of operation in the form of a matrix, we just see what that operation does to the identity matrix. If you're not able to understand this, please look into 3 Blue 1 Brown's playlist on linear algebra, or try to go back and revise the basics of linear algebra. But any sort of linear transformation can be represented as a matrix. Take the identity matrix, and let's say I want to try second row multiplied by 4. I want to see how this looks as a matrix. Let's do it on this. Second row multiplied by 4. Let's try first row multiplied by 3. How's it going to look? That's it. We've transformed these into a linear transformation. If I multiply this matrix by any vector or any other matrix, what am I going to get? X plus 0, x plus 0, right? 0 plus 4y. I got x and 4y. Literally multiplying this by any vector or any matrix for that matter. This is x, a, y, b. Try to see what you'll get. You'll just get the second row multiplied by a scalar, because obviously the rest of the values are 0, and you're just changing the 1 with the multiplied scalar, which we have just taken as 4 or 3. Similarly, for L, do it on the identity matrix. I'm taking the 2 by 2 matrix for simplicity's sake, but this works for n by n, however many you want. Let's try L. Let's say I want to take 3 times the first one subtracted from the second. 3 times the first subtracted from the second. I'm going to get 3, 0, subtract from the second. What are we going to get? Right? Again, maybe 4. What are we going to get? Notice how since this is L, I cannot make the first value smaller than my second. Like if I do 1, 2, then what am I doing? I'm taking the second and subtracting from the first. I'm going upwards. That's not L, that's U. So notice how I'm always doing it like this. I'm always making the first one bigger than the second one. Let's look at U now, how U is going to actually look. Let's try U, 1, 2, 3. What am I doing? Taking the second row, multiplying by 3. Second row, multiply by 3. 0, 3. Subtract it from the first row. What will I get? 1 minus 3, 0, 1. I'm guessing you can probably tell if we change this to 4, what are we going to get? Without even looking, right? We just converted these operations into a matrix. If I multiply this matrix by any random matrix, you'll see that all it does is the exact operation which we did, which is take the second row, multiply it by 3, and subtract it from the first. Try this multiplication by yourself, or try to look into a geometric understanding and see why this works. I'll give you a little clue. For L, what are we doing? Sorry. I'll give you a little clue. For M, what are we doing? We're taking the identity matrix and just multiplying any of these by a random thing, right? So what are we doing? We're taking the identity, taking I cap and J cap, and we're keeping one of them exactly the same and just scaling up the other. Let's say if I change it to 2, 0, 0, 1, right? This would be M1, 2. This would be M2, 2. For this, what am I doing? I cap is scaled by 2. J cap is the same. I cap becomes 2 times. And obviously, this is going to affect the linear transformation by scaling its I cap by 2 times, which basically scales that first row by 2. Same as for the rest of them. All of them, every single one of them can form a linear transformation and can form every single one of these operations, even the fourth one, all of them can be represented as a matrix since they're all linear transformations. Now, this is what we do in Gaussian elimination. We take each of our matrices, AX equal to B. We take A and B, and we perform operations on them. Let's say I perform the first rule, which is multiply. M, what am I doing? I'm multiplying the first row of this entire thing. So basically, I'm adding M here and M here. Since A and B are together, I'm doing it to the whole thing. Basically adding an M here, adding an M here. After that, let's say I do the last rule, which is E. I'm exchanging, I'm swapping. I'm swapping A's maybe third row by the first row, flipping them around. Since I have made the augmented matrix, I have to do the same thing for B. Swap for B's first and third, since I'm doing it on the whole thing because of my notation. So what did I do? I just added an E here and an E here. I'm just adding more and more linear transformations on each side. Now, the fun thing about each of these linear transformations is each of them are invertible. You can find the inverse. They're very basic, elementary operations. They're linear operations. If I'm multiplying by something, I can just divide by it. I can always find the inverse of each of them. All of them always have an inverse. So at no point am I changing the equation. I can always come back. Let's say for normal math, which is not linear algebra, let's say you had this equation. If I multiply the whole equation by 2, I'm not doing anything. The answer to x and y will still be the same. I've just multiplied by 2. We know this. Multiply by 3, 4, as long as I'm doing it on both sides, nothing's changing. And we use this to solve a pair of linear equations in two variables. If you've done the elimination method before, that's exactly what we do. We multiply one by something. That doesn't change it, it just stays the same. But now we can use it to subtract it from the bottom one to make one of our variables 0. That's exactly what we're doing. That's the essence of what we're doing. That's why this is called Gaussian elimination. It's just in the form of matrices. So each of these are elementary operations. They're all invertible. They're not changing our answer space. All of the answers will still be the same. We're just making it easier for ourselves by making the A matrix into a row echelon form. More formally, performing an elementary row operation is the same as multiplying A and B on the left by the corresponding elementary row matrix. Again, exactly what we were doing. We're multiplying both sides by the same thing. You can just keep going. It doesn't matter. You can always go back. Multiplying A and B on the left by any matrix C can only enlarge the set of solutions. That is, any solution x of ax equals b is also the solution of cax equals to cb. Of course, we're just performing an elementary operation. The set of solutions will not change. Notice how it says only enlarge. In fact, it usually doesn't even enlarge it. It just keeps it as the same. The reason it's written as only enlarge is because if we multiply by 0, what are we doing? We're multiplying both sides by 0. We just get 0 and 0, right? So x can be anything now. The answer is infinite. For example, let's say I take the elementary 2-variable equation. If I multiply this by 0, what am I doing? Right? I'm still writing x, but basically everything is 0, right? So it doesn't matter what x is. Everything is going to be 0. If x is 1,000, a billion, it's all going to be 0 since I multiplied by 0. So this is how I've infinitely made the solutions infinite. I've enlarged it. But in most cases, you don't do this. In fact, in Gaussian elimination, we never do this. We don't want to do this. This is ruining our answer. We're just multiplying by something that keeps the set of solutions the same, which is any of our operations, elementary operations. The elementary row matrices are all invertible. Again, we know this. Now, with this newfound knowledge, let's learn how to perform Gaussian elimination to get a row echelon matrix and solve the set of linear equations. Coming back to our initial example, let's try to solve this using Gaussian elimination. Now, the first step to solving this is to form the augmented matrix. Now, let's try to form the augmented matrix directly by just taking A and taking B. A is the coefficients, 2, 3, 4, 2, 2, 2, 1, 2, 1. Make a line for organization, just add B. This is the augmented matrix. Now let's try to form a row echelon matrix. Again, a row echelon matrix should have zeros before the leftmost value of each row. Let's start with the first row. I want zeros below the first value in this row. How do I do that? Well, I can perform the row operations. I can just keep subtracting. Now, what I would suggest is bringing the row with the least value in its first position to the top. So basically taking R3, taking R3, swapping it with R1, or exchange 1 and 3. What do? We're exchanging the rows 1 and 3. So this becomes 1, 2, 1, 3. This stays the same. This becomes 2, 3, 4, 1. What have we done? Just swapped. Notice how both the notations are telling the exact same thing. This is the 3-rule notation. This is the formal notation, which I've taught. Both of them are correct, and you can see them used interchangeably. But you can use any. I'm using both for your understanding. What have we done? We brought one to the top. Notice how we don't have to do this. I'm just doing this because it is simple and clean. But you can do it however you want. It's completely up to you. You're free to use your mathematical knowledge. Now that 1 is at the top, making these two 0 is pretty easy. Use this 1 and make them 0, right? I can't use this 2 to make this a 0 because the 2 is only going to be able to affect these. My L and U operations only affect the bottom rows, and only this can affect this in the bottom row. This can never affect this can never affect this. Again, even for U, only the values above every column can affect that column by the way our elementary operations are positioned. So I'm going to use this one to remove these two. How? I want to make the 2 0. 2 minus 2 is 0. I have a 1, I need to get a 2. That's all I'm doing. I need to multiply the 1 by 2 and then subtract it from that row. Let's do that. R2 is now R2 minus 2R1. Or, since we're going downwards, we're using L. And we can actually use this notation to write the other one. R2 is written first. 2, 1 is written later. And then it's multiplied by 2. That's it. What are we doing? Taking R2 and we're subtracting this. So we're taking the first row, multiplying it by 2, subtracting it from the second row. What do we get? First row multiplied by 2 is 2, 4, 2, 6. It's subtracting it from here. So 2 minus 2, 0. 2 minus 4, minus 2. 2 minus 2, 0. 2 minus 6, minus 4. The last row stays the same. I'm pretty sure you can see what we have to do next. R3. Same thing. Multiply the first row by 2. Again, since we're going downwards, it's L. Multiply the first row by 2 again, which is 2, 4, 2, 6. Subtract it from here. So we get 1, 2, 1, 3. 0 minus 2, 0 minus 4. The last row becomes 2 minus 2, 0, 3 minus 4 minus 1, and 4 minus 2, 2. 1 minus 6 minus 5. That's it. We're one step closer to row echelon form. We made the first part of the staircase. Now that we're done with this, we don't need to use this one anymore. Now what do we need to do? We need to form the staircase. We need to make this a 0. That's it. Then we're done. To make this a 0, we now have to use the one directly above it, this. Notice how we can't use row 1 now. Row 1 cannot be used. Why? Because if I use row 1, this 1 is going to affect this 0. I've used row 1 to manipulate this column to exactly how I want it to be. I should not change this. If I use row 1, since it has a value in this first position, it's going to completely fuck up the first column. So my use of row 1 is done after my first thing. Not that hard to remember. Let's go to row 2. We have a minus 2 here. We need to use that minus 2 to make this a 0. I have minus 1. I need to make it a 0. I need to add 1. I have a minus 2. I need to multiply by something to get 1. So I need to multiply it by minus 1 by 2. That is what we're multiplying it by. So R3 is now R2, sorry, R3 minus minus 1 by 2, R2. Again, you can just write it as R3 is R3 plus 1 by 2, R2, right? Whatever notation we use should be consistent. It doesn't matter if it's minus or plus, right? For me, I'm taking L as minus, but before it was written as a plus. It's up to you. If your convention is to write it as a plus, then your coefficient should be minus 1 by 2, it should be plus 1 by 2, or minus 1 by 2. You can change that accordingly. But again, L because we're going downwards. What are we doing? Taking the second row, subtracting from the third, and we're doing minus 1 by 2. So 1, 2, 1, 3. Multiplying this by minus 1 by 2, we get minus 2 into minus 1 by 2. This becomes 1. This is 0. Minus 4 becomes 2. Minus 1 by 2. Again, that's 2. The rest of it stays 0. Let's do it here. 0 minus 2, 0. This row stays the same. The last row, we're adding 0 to 0. We're adding minus 1. We're adding, what are we adding? 1. So this becomes 0. This 2 gets 0 added. It stays as 2. And this minus 5 is getting 2 added. So it becomes minus 3. What have we done? We have created a row-echelon form. We're done with 80 to 70% of Gaussian elimination. We have done the first part, which is called forward elimination. We just moved forward, kept eliminating. The second part, back substitution. Now, what is back substitution? You can probably tell. We're just going to substitute. Look what we have. 1, 2, 1, 3. 0 minus 2, 0, 4. 0, 2, 0, 0, 0, 0, 2, minus 3. Remember, these rows correspond to a linear equation. So we've transformed our equation into this. X plus 2y plus x is equal to 3. 0x plus minus 2y plus 0z. What the fuck did I make up here? That's a z. Yeah. Is equal to minus 4. 0x plus 0y plus 2z is equal to minus 3. Notice what we've done. 0x and 0y can just be erased from existence, like screw you. Notice what we've done. The last equation, because this is row echelon form, the last equation has become this. We've transformed our last equation into a singular value. We can find z. If we know z, we can substitute it here. I got lucky and like z is 0 here, so we can just directly find y. But if z wasn't 0, we'd substitute it here. We'd be able to find y. Now we know y and z, substitute it here. We find x, we found the answer. All because of row echelon form allowing us to find the last variable. Now you get why it's called back substitution. We're just going backwards and substituting. That's it. That's literally it. We've just solved this pair of linear equations using Gaussian elimination. We found the values of x, y, and z. Now this was Gaussian elimination. Now some books teach you Gaussian elimination, but in fact, it's not Gaussian elimination. It is Gauss-Jordan elimination. Notice how we only used L so far, because obviously this is our main row. We're using this and the above rows to get this staircase of zeros. Again, notice how our elementary vectors, when we were using L, we were getting something like this, where the bottom left was being manipulated. That's what we're doing. We're manipulating the bottom left. Notice how we have U. U is used to manipulate the top right. We can manipulate the top right. We have the power, we have the strength to do it using U. Why would we want to do that? We can make this even more simple by performing a few more matrix operations. Let's say I perform L's and U's and M's such that I get this matrix. So 1 multiplied by x is equal to this. 1 multiplied by y is equal to this. 1 multiplied by z is equal to this. I've just removed every single thing and just made it 1 multiplied by y is equal to this. We directly find the values for x, y, and z. A few more matrix operations to get a simpler answer and remove the back substitution. This is Gauss-Jordan elimination. Some books call it Gaussian elimination, but the technical term is Gauss-Jordan. A row-echelon matrix A is said to be in reduced row-echelon form if, in addition, each pivot entry is equal to 1 and everything else is a 0. Remember, the B values can be anything. These are our actual answers. This is x, this is y, this is z. This is our answer, right? If we have x plus 0y plus 0z is equal to whatever this thing is, let's say 20, then that's our answer. We just have x is equal to 20. We've done it. So continuing with our operations and continuing to perform the elementary row operations to get this leads to us answering the set of linear equations using Gauss-Jordan elimination. Taking our example, let's try to quickly do the same. Let's do the operations that we did before. What we did before, which was basically perform an E, then perform a couple of L's. Now, what do we get? 1, 2, 1, 0, minus 2, 0, and 0, 0, 2. And we got 3, minus 4, and minus 3. So what we got. Now we just need to turn these into 1s and turn these all into 0s. Again, to turn this into a 0, to turn this into a 0, now we're going to look at it's directly below row. We're going to look at the row that's directly below it. So let's use this. Since this is a 0, we want to make this a 0. I'm going to subtract half of this. So again, we're going upwards now. We're using u, right? We're taking the third row, multiplying it by half, subtracting from there. What do we get? Half, half, 1, minus 3 by 2, I guess. Let's leave it at that. This becomes 1 minus 0, 2 minus 0, 1 minus 1, 0, 3 minus 3 by 2, 3 minus minus 3 by 2, which is 3 plus 1 by 2, so 4 and 1 half. Or let's just make it 9 by 2. The rest stays exactly the same. We are pretty close. Just need to turn this into 0. I think you can guess what we have to do. We can only use this. Minus 2, we need to get 2, so minus 1. R1 is now R1 minus minus 1 R2. Again, we're taking the second row, multiplying it by minus 1, and subtracting it from the first. Multiplies by minus 1, we get 2. Multiply by minus 1, we get 4. 1 minus 0, 0, 2 minus 2, 0. 9 by 4, minus 4. Sorry, 9 by 2, minus 4, which is 8 by 2. So we get 1 by 2. The rest of it stays the same. We're pretty close. These just need to be 1. I mean, we have a pretty simple rule to do that. M. Multiply this by R2. It's now minus a half of R2. And like, let's just directly write the next one. R3 is half of R3, right? Multiplication, we're taking the second row, halving it, minus halving it. Again, third row, halving it. That's it. So the rest of the rows stay exactly the same. Second row just gets halved and positive. So this gets halved and positive as 2 minus 3, 0, 0, 2. Now let's go here. Remember, everything else stays exactly the same. Get 2 here. 0, 0, 1 minus 3 gets halved. That's it. What have we done? Converted this into x plus 0 is half. So x is half. Y plus 0 is 2. Y is 2. Z is minus 3 by 2. That's it. This is the same answer which you got before. And now you know how to use Gaussian elimination and Gauss-Jordan elimination to solve any sort of numerical, and you know why it's working. Now, I was going to do a few complicated numericals, but it's been like, what, for a fucking hour or something, so I'll probably leave that to the next part of this video. Thank you for watching. Please leave a like, and I'm too tired for this shit, man. Just thanks for watching.